Building energy simulation tools are helpful in the design stage. They can help test the impact of different shapes and orientation, considering the effect of actual site conditions such as landscape, prevailing wind direction, solar radiation intensities and variations, and temperature and humidity levels. Long buildings have two facades with a very large area and two sides with a much smaller area. These large areas will be susceptible to high heat gain by solar radiation if oriented east and west, much more than if oriented south and north. Depending on the climate and the heating or cooling needs over the year, a different orientation will be preferable. For instance, in hot climates with high solar radiation and high cooling needs, long facades should face south and north. A building can be oriented to exploit the wind direction and speed in order to promote airflow through the building and provide cooling by natural ventilation. Building simulation tools such as computational fluid dynamics, or CFD, can be employed to visualize how the shape of the building will affect the airflow around it. Knowing the predominant airflow patterns around the building will help determine ventilation strategies and size ventilation openings appropriately. The density of buildings on a site will influence the forces of the prevailing wind and affect which natural ventilation strategies will be most effective. Where there is a low density of buildings in an area, air will flow relatively freely through the buildings. In this case, it's possible to enhance cross-ventilation through spaces. In areas with high density of buildings, wind speed between buildings may be low. This would limit the effect of cross-ventilation. However, the higher up in a building you go, the higher the wind speed. This high wind speed can be used to create suction over vertical shafts, increasing the stack effect of vertical ventilation. Now let's look at the same building in 3D and from the view of the plan. Notice that the main wind pattern is from west to east, as shown by the blue arrows. The guiding principles in the building design stage are those of heat retention in cold weather, heat rejection in hot weather, and heat avoidance. These principles are applied in practice through selection of materials and design of the building envelope. In particular, materials should be selected for good thermal performance. That is, they should reduce heat transfer between outside and inside. This means using insulating materials and high-performance glass. As we've already mentioned, glass generally has a low thermal performance than walls. It lets in solar radiation and allows heat to escape more than the walls do in cold weather. For these reasons, the area covered by glass should generally be limited to about 10 to 30% of the wall area, and it should be high-performing. Protection from solar radiation with shading is an important strategy and needs to be designed according to the sun angles and building orientation. This can be achieved with the help of shutters, movable blinds, and vegetation. Infiltration should be controlled by better airtightness of the building. The building envelope is the main source of heat gain and loss. Let's summarize some of the main features involved. U-value. The U-value of a building element determines how much heat transfer will occur through it. The lower the U-value, the better, because the lower the heat transfer through that element. The U-value is a function of the thermal conductivity of each of the material layers in the element and the thickness of the layer. For example, insulation materials have a very low conductivity compared to simple concrete, which is why they help prevent heat transfer and result in a much lower U-value. U-value calculators are available online, where you can test different building element compositions. Solar reflectivity. Finishes that are lighter in color reflect the sun's radiation, avoiding up to half the heat gain you would get through a dark roof. For this reason, in hot climates, wall and roof finishes should be white or as light as possible. Glazing. Glazing typically has a much higher U-value than walls and allows heat entry from direct solar radiation. For this reason, glazing areas should be minimized in hot as well as cold climates. However, windows for daylight and views to the outdoor are desirable, so the size and the design must be carefully thought out in order to optimize these conflicting needs. Thermal bridges. Thermal bridges, also known as heat bridges, are like shortcuts for heat to leak in or out of a building envelope. They occur in weak points of the building envelope, for example, around a window. Around a window frame, the studs, plates, and other framing members act as heat bridges, allowing heat to transfer between the outside and the inside, effectively bypassing the insulation of the wall. These heat bridges can reduce the overall effectiveness of insulation on the facade by up to 50%. The more conductive the framing material, the larger the heat bridge, and the more insulation effect will be lost. Heat bridges can be avoided by installing continuous insulation across the component layer, or with carefully engineered thermal breaks. Another part of the solution is to minimize the number of breaks in the building envelope. Let's talk a bit more about windows and window area. The energy needed for cooling rises significantly as window area increases, as you can see in the chart. Smaller windows can reduce solar heat gain while providing daylight with techniques to optimize daylight distribution. We can optimize daylight distribution through internal finishes and with light shelves, a horizontal surface that reflects daylight further into the room. Lighter colored surfaces on the walls, ceiling, and floor reflect daylight even when overcast, increasing the daylight levels further into the room. Once we have optimized the building design to avoid the entry or loss of heat, we can look to passive systems for their capacity to provide comfort. Even though passive systems may not be able to provide comfort the whole year round, they should be prioritized in order to reduce the number of hours of reliance on active systems, which requires energy to operate. Passive systems for cooling include natural ventilation. Adequately designed natural ventilation strategies rely on openings in the building envelope to promote airflow through the occupied spaces and may offset the need for air conditioning. Natural ventilation has several benefits and strategic options. Firstly, the sensation of airflow across occupant skin alone increases thermal comfort and tolerance to higher temperatures. Secondly, the stack effect can be exploited by high-level openings or chimneys, stimulating airflow across the space, even in the absence of wind. Thirdly, orienting openings to follow prevailing wind patterns will enhance the airflow. And lastly, note that the size, type, and control strategy of openings must be very carefully designed. Evaporative cooling. The evaporation of water draws sensible heat from its surroundings and converts it to latent heat in the form of water vapor. As this happens, the temperature of the surroundings drop. This phenomenon is called evaporative cooling and can be used in buildings by blowing air across a wet screen. While the resultant increase in humidity can be desirable in hot and dry climates, indirect evaporative cooling is better in hot and humid climates where humidity levels are already very high. In indirect evaporative cooling, heat exchangers are used so that no moisture is added to the air. Earth cooling. Earth is good at conducting and storing heat. The lower below the surface of the earth you go, the more steady the temperature. Therefore, earth can be used as a heat exchanger, either to store the cool air, to reject heat removed from the building, or to absorb heat from the ground in winter. Systems can be direct, such as circulating air or water through the earth, or indirect, through the use of a heat pump. Passive heating. Passive solar systems collect and store heat and redistribute it relying on building physics and without fans or pumps. Thermal mass, such as water or rock, and oriented towards the winter sun to collect heat energy. When the sun is gone, the heat is then emitted indoors. Direct gain passive solar systems are useful in cold climates. The systems are placed on the facades of buildings facing the sun, so south in the northern hemisphere or north in the southern hemisphere. The greenhouse effect allows the transfer of shortwave radiation, while the heat generated indoors, which is longwave radiation, is trapped indoors. Passive lighting. Aside from saving on electricity demand, daylight is important for health and well-being. Views of the outside have been shown to boost productivity, mental function, and memory due to the aesthetics and biological effect of being in contact with natural patterns of daylight fluctuations. However, the size of the windows for daylight must also be assessed in terms of their impact on solar gain, as we discussed earlier. These passive system strategies are not new. Traditional architecture generally followed all the principles mentioned. This is apparent when we compare traditional architecture styles from different climates and observe how the response to the local climate was central to the building design. In hot and dry climates, massive walls and roofs are often used for their thermal storage and time lag effect. Windows are small as the sun is very intense. In hot and humid climates, building designs favor ventilation and shading. Modern architecture is a little more homogenized, with lots of tall, fully glazed buildings and no manual operation of windows. These buildings have become common in both hot and cold climates. With no natural ventilation, high solar gains, and large floor plates, active heating, cooling, ventilation, and lighting systems are needed to provide occupant comfort. Passive systems are regaining popularity because of their role in promoting the rational use of energy, the transition to net zero energy or emission buildings, and their positive impact on occupant health and well-being.